Good morning, students. Mr. Carver here. Today we're going to do section 7.8, improper integrals. Now these are improper integrals as opposed to improper fractions, which we took care of first semester and then earlier this chapter. Remember, improper fractions are equally heavy fractions or top-heavy fractions. You take care of those by first long dividing the fraction. These are improper integrals, and here's how they are defined. Improper integrals are where you have an upper or lower bound that is infinite. And I guess I could also add that you could have both an upper and a lower bound that is infinite. So let's take a look at a picture here. Always before we had a finite upper and lower bound. So let's say I have f of x is equal to 1 over x. And typically in Chapter 5, we would go, say, from 2 up to some finite number, say 7. We'd integrate, plug in the upper, the lower, subtract, according to the first fundamental theorem of calculus. Now what we have is a case where you take out the upper bound. So now I'm going to be finding the area between 1 over x, the x-axis, going from 1 or 2 or whatever that lower bound is, all the way to infinity. Now, it may seem logical to assume that if I go from 1 all the way out to infinity underneath a curve, I'm going to get infinite area. But interestingly enough, that's not always the case. If you think about infinite series, when you're adding numbers together, for instance, if you've got 1 plus a half plus a fourth plus an eighth, then you add all those together. Even though those numbers get infinitely small, the rate at which those numbers get small determines whether this sum stops growing or continues to grow. The term for that was to converge if it actually stopped growing and to diverge if it continued to grow without bound. The same thing applies to area underneath the curve. It actually depends on how quickly your y values get small. Looking at an area underneath a curve, though, it depends on how quickly this curve approaches the x-axis. If this curve approaches the x-axis quickly enough, the area will be finite. If it takes a more leisurely approach to get to the x-axis, then the area will be infinite. Now, the way we're going to determine that is through integration. However, there are other cases where you've got an improper integral, and let me add to this list. An improper integral is also defined as one that has a discontinuity at either endpoint of integration or within the interval of integration. So if I take a look at the graph that I had before, let's say it's 1 over x, vertical asymptote at 0. We'll call it f of x. If I have an interval of integration that has a discontinuity at one endpoint, you might be looking at something like this where you integrate from or out to, say, 2 from 0. So this right here, in this case, you would have a discontinuity at the left-hand endpoint. Let's say that I have a discontinuity within the interval of integration. You might be integrating from, say, -2 to 2, where you've got a discontinuity right at x equals 0. And again, the way we're going to determine whether this area is finite or infinite is through integration, and that's what I'm going to show you in this section. By the way, if you look at this picture that I have right now, you have the same problem as when you had an infinite upper bound of integration, because this area is contained in here. You've still got that behavior, that asymptotic behavior now along the y-axis. The question is, does this curve approach the y-axis quickly enough in order for the area to stop growing? And again, that's what we're going to be looking at in this section. All right, let's work a few problems. We'll take a look at 2 problems I think that illustrate this concept fairly well. Let's say I'm integrating from 1 to infinity of 1 over x squared. The technique that we're going to use is, well, it will involve limits, and here's how. I'm going to change that upper bound to, say, a, and I'm going to drive a to infinity. And again, I can't have quotients, so I'm going to bring that x up to the top. X to the negative 2 dx. I'm going to integrate. It gives me negative 1 over x, evaluated from 1 to a in this case, taking the limit as a goes to positive infinity. And now, according to the first fundamental theorem of calculus, I just plug it in. I now get 1 over a minus a negative 1 over 1, upper minus lower, taking the limit as a goes to infinity. Negative 1 divided by huge is 0, minus a minus 1 gives me an area of 1. So that area stops growing, even though I integrate from 1 out to infinity. This area is said to converge, and it converges at 1 unit of area. We'll take a look now at one that maybe gets there a little more leisurely. Let's say I go from 1 to infinity of just 1 over x dx. Again, what I'm going to do is take that upper bound, turn it into a variable, and I'm going to drive that variable to hugeness. That is x to the negative 1. Remember, when you integrate x to the negative 1, I get the natural log of the absolute value of a, now evaluated from 1 to a. Excuse me, that's the natural log of x. Evaluated from 1 to a, according to the first fundamental theorem of calculus, I take the limit as a goes to infinity of the natural log of a minus the natural log of 1. Now, if you think about the natural log graph, again, it looks something like this. I take the limit of that graph as I go out to infinity. That does, in fact, give me infinity, minus then the natural log of 1, which is 0. This area is infinite. So this is said to diverge. You have a divergent area. Now, these graphs look very similar going from 1 to infinity. 1 over x squared looks something like this. 1 over x looks something like this. They both go to 0 as x goes to infinity. However, the red curve, 1 over x, gets to the x-axis much more leisurely than 1 over x squared. 1 over x squared gets to the x-axis very quickly, so the additional area that you're adding on is negligible, creating a convergent area. All right. These, of course, get a little more difficult. All right, let's say I have this, the natural log of x, going from 0 to 1. Now I have a left-hand endpoint that is undefined, rather, not indeterminate, it's undefined, and that is at 0. So I'm going to use the same technique. I'm going to then change 0 into a variable. I'll go from 0 to 1, but now I'm going to drive a to 0 from the right. Remember, I'm going from 0 to 1, so I want to approach that vertical asymptote from the right-hand side. All right, now I just need to integrate the natural log of x, and of course you remember that we don't have a formula for the natural log of x, so I'm going to use integration by parts. My u is the natural log of x, my dv then is dx, so my du then is 1 over x times 1 dx, and my v is equal to x. So I've got u times v, that is x, natural log of x, minus the integral of v du, that is going to be 1 dx. So I get x ln x minus x, evaluated from a to 1. According to the first fundamental theorem of calculus, I'm going to take 1 and plug it in there. I have 1 times the natural log of 1 minus 1, minus then a. Actually, I'm running out of room. Hang on, I need to rewrite. All right, now we're cooking. So I take 1 and plug it in. I get 1 times the natural log of 1 minus 1, minus a times the natural log of a minus a. So here we go. I take a look at the first one here. I've got 1 times the natural log of 1. That is 1 times 0. This gives me 0 minus 1 in the first set of parentheses. Now I just need to figure out what the second set is equal to. So now, if I take the limit as a goes to infinity, I take a look just at this portion right there. If I plug 0 in for a, I get 0 times the natural log of a very small positive number. If I look at the natural log graph, the natural log of a very small positive number, so approaching 0 from the right-hand side, you can see gives me negative infinity. 0 times negative infinity, people, is indeterminate, which means I've got to do something to this green circled expression. So I'm going to take the natural log of a, and I'm going to take the other a, and I'm going to move it to the denominator. Now if I take the limit as a goes to 0 from the right-hand side, what I get is negative infinity on the top, and I'm going to get positive infinity on the bottom. That is indeterminate, so now I'm going to use L'Hopital's rule. So this gives me 1 over a times 1 on the top, and negative 1 over a squared on the bottom. I'm going to copy dot flop. That gives me negative a squared over a. Those cancel, and I get 0 for my answer, which is determinate. 0 over 1, really. It's not 0 over 0, it is 0 over 1. So this first part right here becomes 0, minus the limit as a goes to 0 is 0. 0 minus 0 sounds like it could be indeterminate, but it's not on the list because we have it memorized. So this part does go to 0, and my limit then is negative 1. It's negative 1 minus 0, and this is my answer, which means it converges. And converges just means it is finite area. So if I get rid of some of this stuff here, and just tie this into what I'm dealing with picture-wise, conceptually, the natural log of x in going from 0 to 1 looks something like this. If I integrate from 0 to 1, I'm talking about this area right there. And that graph of the natural log of x approaches the y-axis quickly enough in order for the area to stop growing. It's also, incidentally, below the x-axis, which is why I'm getting a negative area figure, negative 1. All right, let's take a look at this problem. I've got 1 over the cube root of x minus 1. You got to really be careful on these guys, because as you look at the area, if you look at these integrals, you have to pay attention to discontinuities. 1 over the cube root of x minus 1 is undefined at x equals 1, which is within my interval of integration from 0 to 2. You must split it at the discontinuity. All right, so let's go ahead and do that. What I'm going to do then is split it at 1. This original integral then is going to go from 0 to 1. I'll let a equal 1, and I'm going to take the limit as a approaches 1 from the left-hand side, because remember, I'm approaching 1 from the 0 side, the left-hand side. And this is going to be x minus 1 to the negative 1/3. I might as well get rid of the quotient while we're at it. I'm then going to add this then to the limit as, say, b approaches 1 from the right-hand side. And again, I'm coming in from the right because I'm approaching it from the 2 side. I'm coming in from the right-hand side. Again, it is the same then antiderivative dx. All right, here we go. This will allow me then to very carefully examine the behavior of the area on either side of my vertical asymptote. All right, here we go. Power plus 1 over power plus 1. That's going to give me 3/2 x minus 1 to the 2/3. Going from 0 to a, again, taking the limit as a goes to 1 from the left. I'm going to add that then to 3/2. This is x minus 1 to the 2/3. Now going from b to 2. All right, according to the first fundamental theorem, I'm going to plug in a first. And a is going to 1, so this is 3/2 times 1 minus 1 to the 2/3 minus 3/2 times -1 to the 2/3. That's 0 minus 1. By the way, I can do this, right? I can just take a, that value of a, which is +1, and plug it directly in. I only need to look at behavior if I get an undefined function. All right, so this first part goes to 0. This next part is negative. This is actually 0 minus 3/2. I'll just write it like that. I'm going to add that then to what I get when I plug in 2. This is going to be 3/2 times 1 to the 2/3. Sorry for the handwriting, guys. And this is going to be 3/2 times 1 minus 1. That's 0 to the 2/3. So this is plus 3/2 minus 0. All right, and what I get is -3/2 plus 3/2. I end up getting 0, but here's what I notice. I notice that both of these are convergent. So 0 makes sense. I've got finite area below the x-axis and finite area above the x-axis. Arithmetically, they offset to 0, but this is convergent area. I've got offsetting finite areas, which means the overall area is, in fact, finite. By the way, if either one of those would have been infinite, it would have diverged. Let's take a look at another. Or, by the way, I guess I should mention if both of them are finite, or excuse me, both of them are infinite, it would have diverged. Let's take a look at one that looks maybe a little like that. All right, here's a function that has no discontinuities anywhere along the x-axis. However, in this case, I have infinite upper and lower bounds. So here's what you need to do. In order to clearly see what is happening on this and to avoid any incorrect conclusions, you need to arbitrarily split this interval if you've got upper and lower bounds somewhere along the x-axis. It doesn't really matter where you split it. I generally pick 0 because it seems to be fairly easy. So I'll split this at 0, and what I'm going to do then is I'm going to integrate from, let's say, a, and I'm going to drive a to -infinity. I'm going to go to 0. Again, I'm arbitrarily picking 0. I've got e to the x over 1 plus e to the 2x dx. I'm going to add that then to the area from, say, 0, again, where I arbitrarily split it, all the way up to b, and then I'll drive b to hugeness. E to the x over 1 plus e to the 2x dx. All right. I don't know if you can recognize this, but these are actually going to be arctan functions. My a is going to be 1. My u will be e to the x. My du then is also e to the x dx. So when I anti-derive this, I'm going to get 1 over 1 times the arctan of e to the x over 1, going, in this case, from a to 0. I'll add that then to, again, it's the same antiderivative, the arctan of e to the x over 1 times 1 over 1, now going from 0 to b. All right, here we go. According to the first fundamental theorem of calculus, plug in 0. That means I have the arctan of e to the 0 minus the arctan of e to the a. Add that then to the arctan of e to the b minus the arctan of e to the 0. All right, take these one at a time. The arctan of e to the 0 is really the arctan of 1. The tangent, and by the way, arctangents are actually angles, right? So the tangent of what angle gives you 1? That's pi over 4. That comes all the way back from trig. Minus then e to the -infinity. And e to the -infinity, I'll write this over here, e to the -infinity is the same as 1 over e to the infinity. So that's the arctan of 0, and the arctan of 0 turns out to be 0. All right, so get rid of that. Let's continue on. Now I've got the arctan of e to the infinity. E to the infinity is in fact infinity. Now here's the deal. What you're looking for is an angle that gives you an infinite tangent ratio. Also, think about the range of the arctangent coming from first semester. The range of the arctangent only goes from -π/2 to +π/2. So when I'm talking about the arc function, by the way, this is a graph of the regular tangent, right? But just to get my head around it, I'm looking for an angle that gives me infinity on the regular tangent curve. And you can see it's going to be π/2. Minus then arctan of 1, which is going to be π/4. By the way, remember that I said that it didn't matter where you split it. I think it's obvious when I start evaluating this that it doesn't matter where I split it, because this value here will always be offset by that same exact value there, right? This will always match this, and they will always cancel, which leaves me then with π/2. This is convergent area, which means I've got finite area between this curve and the x-axis going from -infinity to infinity. Now, let me say this again. When you split this, if either one or both of those individual evaluations, that is this or this, if one or both is infinity, it is divergent area. It is actually infinite area. And it doesn't matter if the area is offset, right? You could have plus and minus infinity. You are adding together two infinite amounts of area, which means the area diverges. I hope that's clear, people. All right, also be looking for, when you evaluate these, indeterminate form. You've got to use L'Hopital's rule to get those things evaluated. I'm hopeful that this is enough to get you through tonight. I'll certainly answer questions and help you with this as time passes. Thanks much, people.